Hello, everybody. Welcome to the webinar, Combining AI plus HPC for Real-World Breakthroughs, presented by Google Cloud and Rescale, where we will talk all things exciting AI HPC, including new capabilities, use cases, and future possibilities. My name is Jolie Hales, and I will be your moderator today. And as we're waiting for people to trickle in, we did want to put a little plug in for our podcast called the Big Compute Podcast, which is presented by Rescale. And it shares stories about basically how engineers and scientists, just like many of you out there, are changing the world through computational simulation. And it's on top charts around the world of being hailed as the Radio Lab of engineering. And we wanted to give you, as we're waiting for people to trickle in, just a sneak peek of what that podcast is like. So hopefully this plays. Go gadget.
What can computational science tell us about the tsunami generated by the biggest earthquake to ever hit Europe? Before you know it, everything is shaking, and shaking loudly. What makes the coronavirus so contagious?
It's the machine that literally will latch on to your human cell and ultimately infect you.
And what was it like when a massive act of cyber warfare stopped an entire country in its tracks? Their ATM greets you with red text over a black screen. This is really starting to creep you out. These are just some of the questions being answered every day through the power of computing. And on season 2 of the Big Compute podcast, we transport you to the heart of these stories, giving you a first-hand look at how computational science is changing our world. Find the Big Compute podcast wherever you get your audio, or visit bigcompute.org.
Yes, that is my voice on the podcast. Apologize for always feels like shameless self-promotion, but we do think you'd enjoy it. And Google Cloud was also a sponsor of the last Big Compute conference, which you can learn more about that conference, as well as the podcast at bigcompute.org. Okay, without further ado, let's introduce our speakers. Our first presenter today is Massimo Maccaro from Google. And a little bit about him, he's part of the Office of the CTO at Google Cloud, where he helps customers reimagine their businesses by leveraging the power of AI and Google products that enable it. And Massimo has a background in theoretical physics and a PhD in computational neuroscience. I love that I get to work with such intelligent human beings. And then after Massimo, we'll hear from Dosh Akaiden of Rescale. And a little bit about Dosh, he manages a team of engineers responsible for ML workflows and GPU accelerated virtual desktop solutions. And before joining Rescale, he was a research scientist at, you may have heard of it, NASA, Ames Research Center for several years, where he contributed to the development of next generation air and spacecraft. He has a PhD in mechanical engineering from CUNY and a postdoctoral training at Stanford. So at this time, I will go ahead and turn webinar control over to you, Massimo, and let's get this show on the road.
And all right, thank you so much, and nice to meet everyone here. Thanks for having me. So I'll start from a quick introduction to the topic at large and try to kind of set the context. So first of all, I want to just kind of acknowledge that the topic of applications of AI to HPC is absolutely not new, and it started to make headlines already for a number of years now. Although actually, I would say that it's also increasing steadily, and the number of applications and the impact of those applications is actually very exciting, in my opinion. And we'll actually cover some topics today about that. But let me kind of also set a little bit of context of what we mean by applications of AI to HPC, because there are many levels and many ways of thinking about that. The way in which I like to conceptualize is that there is almost like a maturity model. There are very obvious things that have been going on in the HPC world for quite a while. And actually, there are much more advanced topics that are still kind of in the domain of research. So let's start from the top of the stack here. So I think actually kind of a lot of people that work in HPC at this point have used in one way or another some form of accelerators in the context of HPC workloads. A lot of these accelerators nowadays, because of the market trends, are optimized for AI workloads. So GPUs, of course, is the most important example there. but also other accelerators. I'll talk later about some of the Google propositions in TPUs, tensor processing units. So that's really kind of, I consider it almost like a basic entry level of what you could do with AI assets in the world of HPC. Now, if you go one step below, you can also think of using AI to optimize the HPC workloads themselves. So things about schedulers, storage allocation, cache optimizations and things of that kind. And that actually kind of is a very less talk about and less fancy, if you want, but extremely impactful kind of applications of AI to HPC. AI can actually kind of accelerate a lot of these workloads by actually just kind of work at that level. Now, as we go one level beyond, and we'll spend a lot of time today talking about that, you can think of building AI surrogates of scientific models. The idea is that instead of trying to solve, if you want, kind of with numerical models, the equations of physics or chemistry or biology that you're trying to kind of solve for your particular problem, you use AI to find fast solutions, shortcuts, if you want, to those problems. And this is extremely effective and is actually dominating in a lot of use cases nowadays, at least in the research world. And then finally, and we'll touch in the final part of this talk a lot about that, you can think of building AI models that are physics informed. And this is extremely exciting for me, coming from a physics background, because this actually allows you to take the best of both worlds. Use the extensive knowledge of physics that we have developed over centuries, but then actually you also use the power of data and AI in terms of discovering patterns and leveraging those physics laws to bring them actually one step beyond. I'll just kind of go very quickly. I just want to get out of the way this idea of GPU, and we'll have actually a lot of examples later. But again, everyone I think knows graphic processing unit, GPUs. They're often faster than conventional processors, but actually they're also much more efficient from an energy perspective, and that very often results in some cost optimization down the line. So it's not always necessarily a speed up play. Sometimes it may also be like just like a power play or a cost optimization. And we'll talk later. I mean, on the right here, you see the third version of our tensor processing unit in Google that actually has been dedicated for AI, but I think actually has a lot of potentials for high performance computing workloads as well. Tensor in tensor processing unit basically means metrics, and those are devices that are really optimized for linear algebra. That is really kind of at the core of a lot of HPC workloads. So there are a lot of like parallels there. Now, a lot of people often I hear, well, I mean, GPUs are very expensive or they're hard to get. I just want to make an example. This is just the Google Cloud offering. Today we have a very, very wide variety of GPUs. All those are available for rent, like you literally pay by the second you use them. We have actually some of the most modern devices, like the Nvidia A100s, are available on Google Cloud. They offer like tremendous performance. We can kind of offer machines with 16 of those together in a single machine. But also we have very, very cost-effective GPUs. So there is actually a lot of availability for all the kind of needs and targets that people may have. And those are pretty easy to recruit and rent, even just for a few minutes on the cloud. Now, of course, that's not the only way to use GPUs, and especially like in HPC workloads, and a lot of supercomputers and big HPC cluster today actually are starting to kind of embed GPUs extensively because actually of their capabilities. Moving on, I just wanted to give an example of what I mentioned actually as the second level, using AI to optimize HPC. So for example, within Google Cloud, we do that all the time. We recently announced actually these features where we will use AI models to optimize your clusters and effectively kind of scale them in and out. So the interesting thing here is that the AI is not just able to react to changes in load, but it's also able to predict. And so in a sense, you see actually here on the right, you have like the normal curve of like a normal auto-scaling system, where actually as you hit a particular threshold, you automatically resize your cluster. That actually presents problem because very often, if you have like sudden jumps, you may actually kind of overload instances, or you may actually kind of even kind of miss traffic sometimes, or kind of slow down some workloads. When you go predictive, you can actually learn much better, for example, temporal patterns, seasonal patterns of your usage of your cluster and be much more efficient in the way in which you auto-scale that cluster. There's even kind of more involved things. So for example, here I put a link to a research paper from Argonne where they have actually kind of applied this to supercomputer scale. So I think actually that's actually a very promising area, especially the scheduling world. Talking about very quickly about surrogates, again, we'll have actually a bunch of other examples later. We at Google have been successful in applying the idea of building a surrogate model to a very complex simulation to a lot of areas. One of my favorite ones is weather predictions, where models in weather predictions are often extremely complex and very hard to compute. So for example, some of the state-of-the-art models will take 8 hours to run given a particular initial state. So that means that your forecast is only available 8 hours in the future. And actually presents a model because it means in your simulation, you're only able to incorporate data from 8 hours before. So, one of the work actually of Google AI has been about effectively building a surrogate model for some of these simulations and then working at a very small scale and actually having a very good accuracy in the prediction. So again, I consider this as a very advanced example because those simulations are extremely complicated, but it's very interesting because if these surrogates are able to work at this level of difficulty, you can imagine actually they will also work in other simpler domains. A more fun example, this is from Ubisoft, is about kind of, simulating physics, for example, in this case of a cape. And you see kind of how these figures work very similar. So what you see on the left is a full kind of simulation based on kind of normal numerical techniques, and it's running about 2 frames per second. On the right, you see AI accelerated simulations running at 3,800 frames per second. So you may actually say, well, I mean, like, why does that matter? I mean, I don't need actually that kind of speed. But actually, what that allows you is that then actually you can take that to the next level and simulate a lot of these things. So this simulation is now running basically in real time at 240 frames per second, and you have a number of objects, each one simulated. By the way, I think actually this may come a little bit choppy on your screens. So sorry, that's actually is the result of the webcast. I put actually the links of some of these papers, and you can actually go check them out actually in full details and resolution. But this actually is very fluid as they run it in real time. So that's very important because it allows you to do more with the same compute or the same constraints that you have before. And then one last example I'll say is that in a completely different domain, another example from Google AI has been application of this kind of ideas to chemistry modeling, and in particular kind of predicting properties of chemical compounds. And usually the normal way of doing this is through like a very complex quantum mechanical simulation called density functional theory. And that actually takes thousands of seconds for any molecule to run. The applications of AI, in particular, some of the techniques of message passing, has allowed this actually to run effectively in tens of milliseconds. And that actually is about a 300,000 speed up. So there are very few things, honestly, like in my career, where you can have 5 orders of magnitude of a speed up using a technique instead of another. So I think this actually, again, kind of talks about how important this is in this area. And one last thing actually I'll mention is that this is not just about completing workloads faster. It's also about solving much harder problems. We'll talk maybe a little bit more later, but very often what people do in HPC is that they don't try to solve the forward problem. They try to solve the inverse problem. For example, in this case, I may want to find a compound that has certain properties. I don't know which compound that is, and I'm basically searching in the space of compounds. So what I can do with these surrogate models is have a very quick search, because actually each compound that I try, it's very fast to simulate and actually converge very quickly to a very good region of my state space. And at that point, if I don't trust that surrogate, because sometimes they don't have actually the same accuracy or reliability or generalizability of the full models, I can still run the full model on top of that to kind of make sure that that particular point that I converged is what actually I want. But actually, this allows to have much faster search and kind of solve these invert problems, or in another environment they're called generative modeling and optimizations. So this actually is a very important thing actually to keep in your mind as you solve this. And for example, this technique is currently very popular in the pharma world. So with that said, I'll hand it off to Dosh that will carry us actually into a number of more specific examples.
Okay, thanks Massimo for the intro. I'll talk about the state of HPC and AI today and why that matters. I will pose first what problems are we trying to solve and why AI and HPC the GPU acceleration matters. I'll start with this classical study that was done in 2014 by several people from NASA and industry and academy. And so in that work, you can refer to that in the reference. They identified 6 key problem areas and proposed revolutionary program to identify each of these issues by 2030. And some of the prime problems here is the scalability of compute, geometry, and grid generation bottleneck, and being able to do what Massimo just described, this inverse problem, and novel approaches in numerical algorithms and physical modeling. I'll start with acceleration aspect, HPC acceleration aspect here. Today, if you visit this website, Nvidia lists nearly 1,000 GPU-enabled engineering simulation apps. A lot of these are in CFD domain, and we can take a look how do they stack up in terms of performance and cost benefit. So even if you look at the most basic approaches here, like converting a traditional CFD algorithm or known and true workloads algorithm to work with GPUs, you see less than 10x GPU acceleration here. And even then, the authors here mentioned that it does make financial sense. Yes, GPU nodes are expensive, but still there's a win around cost performance. And if you look at a commercial example here, the availability of GPU acceleration allows for live solution feedback. So this allows you to quickly design and like search through design space in an interactive manner. And then if you're not sure about the final result, you can always get the higher fidelity solution. That also GPU accelerated fashion. So up to like nearly 4 times GPU acceleration on Fluent in this case. It's cited. If you go back and decide to start from scratch and do a GPU first implementation rather than retrofitting an existing code, then you can achieve 10x or more speed up. And this is an example we have on the platform. Turbo Stream Code is primarily a turbo machinery simulation program, and they cite 32x or more acceleration here. And even more highly parallelizable or meshed algorithms deliver even more scale up here. And from these companies, we do actually see the address of the price point issue. For instance, if you don't even look at the pricing here, you can see versus an 8-core machine, even a relatively old GPU machine goes up to maybe 5 times speed up, 99 hours versus 17 hours. And the speed up per price is actually at 10x. So you're actually not only doing much faster, but also doing the same simulation much cheaper for using a very rudimentary GPU hardware here. And continuing on with this highly parallelizable algorithms, we have particle works, for instance, and that does similar to previous codes, and ray tracing algorithms on heat transfer, radiated heat transfer. Now we are talking about 100x faster than what is done on GPU. So in all these cases, we can clearly see that cost benefit is out there. There's no question of, it's a matter of your application, sure, but most applications actually deliver on your financial goals too. Yet another example here is the AceCast, which is a GPU-ified version of WARF, the weather forecast code. And one node of a CPU is taken here as a baseline. And one GPU, not a GPU node, a single GPU is already twice as fast and maybe half of even more cheaper than that single node of CPUs. And this goes even better if you have higher number of GPUs present. So GPUs are cool, acceleration is great, but where is AI here? How does it benefit the engineering workflows? There are currently two main approaches that are already hitting commercial markets. This has been around for decades now. The first one is the data-driven and supervised approach. So basically, you build a surrogate model using a variety of machine learning tools. And it only recently started including deep learning, but PCA, kriging, these have been around for decades. But in the end, what you do is you ingest a set of labeled data, either from the field or from simulations. And then you go into a design and optimization cycle. So that prediction and acting on prediction completes the whole circle of artificial intelligence here. So you can build an intelligent cycle which improves or changes the design as you wish. If you ever question an outcome of the cycle, you can always verify. You can run a higher fidelity simulation, as Massimo also mentioned, just to check if that prediction is correct or makes sense. And then finally, you can manufacture these prototypes and then feed back that information, the additional information from physical world, back into your surrogate model using test data. This is where we talk about IoT and digital twin. There's the more lower level implementation of machine learning techniques that's coming up since the last 4 or 5 years around. So in the previous approach, the surrogate model is agnostic of the simulation, the physics, underlying physics of the problem. All it sees is a set of data and try to regress a model of it. So where has my physics gone? Where is the information, the expertise we have since from Newton for centuries is gone? So this approach identifies that problem by incorporating the PDEs that define the physical phenomena into the neural net itself. You now become truly physics-driven. So your neural net no longer considers any unphysical data. It self-generates and in a consistent manner with the physics. The key advantages here that I want to point out is that inputs are point clouds here, is not mesh. And the outputs are not simply a solution field, but it's derivatives. What it allows are the following. If you circle back to the issue that we mentioned in the first slide of this section, is that point cloud allows you to basically have a easier time on mesh generation, because there's probably no mesh generation involved. It's just point cloud, and then that allows for not having to clean up a CAD model more vigorously, and being able to generate this point cloud as more automatic and less human labor intensive. So that identifies this challenge area here. Availability of derivatives allows you to do this inverse problem and multidisciplinary design and optimization. And solving a problem using this neural net is a novel approach here that affects both HPC side and the numerical algorithm side. And let me explain why. The previous acceleration slides, we mentioned that we are always trying to fit a solution to existing hardware, try to retrofit or come up with novel implementations of existing approaches to whatever hardware we have today, GPUs and TPUs. What if we approach the problem using a tool that is already proven to be efficient on GPUs? Neural nets are prime examples. They are shown to be efficient on GPUs since like web services, boom of web services, and the image classification, ImageNet, and all that. And this is known. And why not try to use that in this context, so that instead of trying to find a solution one way, you apply a solution that is known to be working in another area to this problem. So that is really exciting, and I maintain that this is a revolutionary approach that is probably needed in identifying these areas of problem. Let me give an example on this somewhat generic discussion. So Nvidia Simnet is publicly available and can be used by anyone basically. And one example here, we are seeing a relatively complex geometry here being simulated using this neural net. All you put is a geometry that creates the point cloud by this library, and then the solver predicts the outcome. If you look at this reference here, these are the side-by-side comparisons of this actual CFD simulation versus the neural net prediction. And for all means and purposes, these predictions are accurate enough for doing a design cycle or engineering design. An example from commercial providers of artificial intelligence for engineering workflow. We are at least aware of two platform providers that provide an machine learning model generated specifically for a given use case or customer, and then available for real-time design. In this case, Monolith AI has a service that allows the designers to change the design space and get the results at real time, similar to ANSYS Discovery Live, but has a machine learning engine behind it. Similarly, Neural Concept has the same approach, and then you can actually integrate their service into the tools that you are probably using today, in this case, ParaView. So what this allows is that instead of waiting for 2 hours for the result of a CFD simulation, you get that nearly real time in 50 milliseconds. Is that accurate? That's accurate for a given purpose. And if you ever are not sure, you can always do a high fidelity simulation, like wait 2 more hours and make sure that your expectations are met in terms of accuracy. So the disruptors here implementing this kind of advancements in science and engineering, and big players are responding. This is a publicly available YouTube video by CTO of ANSYS. that shows their goals of implementing the physics-informed neural nets and other ML-based PDE solvers into their arsenal of tools, simulation tools. In the next few years, I expect other big players, maybe they are already implementing this kind of approaches into their set of tools, commercially available for design engineers and simulation people. I would like to proceed with some notable examples of AI and ML on Rescale. This customer from Korea, Dosan Heavy Industries, is actually a partner of both Google Cloud, and Rescale. What they do in this particular case, in one of the cases, is non-destructive testing of industrial parts using machine learning techniques. Rescale is a compute platform primarily, and they do the data synthesis and machine learning training on Rescale platform. And then once they have that, they serve that into field for like other shops and testing facilities using Google Cloud infra. So they again use the compute resources of Rescale and use IT resources and basically web services from Google Cloud to effectively test their product at scale. Another customer we have from Korea, again, Aesop Bio. They do drug discovery. They actually develop a framework that is aimed to be available for other people. They are developing this framework for disease screening, drug discovery, or design and efficient efficacy prediction of the drugs. So they are using again deep neural nets to achieve this goal, and they run on GPU instances. Another one, we had an independent researcher, Jacob Farhak, who put together a data mining project for transmission of COVID-19. This is a few months back when actually COVID first started. And he has been using a Dask node, Dask scheduler to utilize multiple GPU instances running at the same time to generate to run the simulations and generate the results of the transmission, COVID transmission. The paper is there in the references. And we have numerous other customers who use AI and ML tools today installed on Rescale platform. We won't be able to name all of them, but people familiar with the matter would probably guess some of these big names. So these customers are leaders in their industries, respective industries, in automotive, aerospace, electric cars, and autonomous vehicles, pharmaceuticals, and all these areas. So if you're interested in using Rescale platform for those purposes, I will talk about that after I hand it over for Massimo to tell us what's possible far out there.
Thanks so much again, and thanks, Dosh. I think those are really, really exciting examples of what is possible. So in this last part of my intervention, I wanted to bring you a little bit into the realm of what's coming, and also hopefully trying to give you some intuition of why the speed ups are kind of disproportionate in some of those environments. So let me start from being a physicist. One of my favorite topics. So I do strongly believe that partial differential equation, PDEs for friends, effectively kind of run most of nature. And a lot of processes are described by PDEs. Now, the traditional way of solving PDEs numerically always goes through a step of discretization. So whether we build uniform grids, very complex dynamic meshes, usually we approximate the continuous physical world that would be unsolvable with a discrete version of it. And then we try to solve the discrete version. However, the problem is that for most problems, when you work with three-dimensional spaces and you add the dimension of time, that effectively gives you like a fourth dimension of your gridding. That means that any problem will scale with the power of d+1 if d is your number of dimensions. For example, if you're trying to do a three-dimensional simulation, that would be a power of 4 in the size of your grid. So this actually is an example of like in weather forecast, this actually is state-of-the-art weather models. And when you really take into account this necessity of discretization and the scaling law, very often a lot of simulation have to run with very coarse grids. Or if they run at very fine resolutions, they start taking a very, very large number of resources. Here I have kind of, simplified in a very kind of simple example, how this scaling laws really works. So if you have, let's say, a grid of 100 kind of linear elements, and you're in 1D, that's a super easy simulation to run because you're really dealing with something on the order of 40 kilobytes of memory. But already if you start to kind of amp this up to three-dimensional spaces, now you're talking about a 400 megabyte. Now that's still kind of very much in the realm of even a laptop today in terms of simulating something of that kind. But you see, as soon as you start stepping up your resolution, the d+1 scaling law really kills you. And by the time you've got to like 10,000 linear elements and you're working in full 3D, you really need a supercomputer in order to simulate that. And everyone that works in HPC and physical simulation know this very well. Now, why can AI help here? Well, if we were able to reduce this gridding size by just a factor 10x, that's a lot, that actually would mean, for example, in a three-dimensional case, 10,000 times faster and smaller simulation. So that kind of really changes it from a supercomputer to a normal machine that people may have in a lot of cases. So that's why it's so transformative. Now, you may say, well, why would I be able to kind of reduce the resolution so much and still kind of maintain my accuracy and my stability of my simulations? Well, part of the reason is that when we work on those grids, and again, this I promise is going to be the only piece of math actually on those slides, what we really do is that we approximate a differential operator inside these partial differential equations. And very often we approximate it in some kind of first, second, maximum third order approximation of that operator. And this actually is done basically with very simple numerical techniques. Now, this is very, very effective, but again, it doesn't allow very often to make those grid sizes very small. What we could imagine of doing is instead actually taking a neural network to try to learn how these grids behave looking at a larger environment. So if you want to take like a high resolution, like in the image on the right above that actually you would simulate normally, for example, that's a two-dimensional turbulent furrow. And now you do an exact coarse graining of that simulation and you try to simulate that. Now, if you do it with normal technique, what you would experience is some kind of diffusion, as is seen actually in the rightmost picture, where if you want your simulation kind of very, very quickly diverges. However, if you apply a neural net to learn those differential operators on those coarser grids, you can get very, very accurate results even on those coarse grids. And this actually is a super interesting insight that can change quite a lot how we think of running this simulation. So again, in my previous slide here, I have a paper on PNAS that has been published recently where we show some of these examples. But this actually is really kind of one of the core ideas here of why those AI techniques actually allow these speed ups. Again, as I said, they are preposterous in a lot of environments. Now, you can even go one step beyond, as you know, like in a lot of situations, you either don't want to have a uniform grid or that's not convenient. For example, you may have very inhomogeneous spaces where some areas require very, very high resolution, some areas don't require it at all. So a lot of people use meshless simulation, and those actually mentioned some of those. One interesting kind of aspect, this actually is work by DeepMind from last year, is to think of like the space of the different connected objects in the physical world as a graph, and then apply techniques of graph neural networks to simulate, to learn how those different particles interact one with each other, and then to simulate them. And they've got incredible results in this work that, again, I encourage you guys to kind of look more carefully. I'm gonna just kind of here playing like a cool video of what they're able to do. And again, sorry, it's choppy. It's the usual problem, but again, you can kind of look it up on the paper and find a full resolution video. The thing that amazes me here is the ability of those models to capture very, very complex physics, even working at this kind of, in these approximations. And part of the reason is that this models actually are trained on a lot of these simulations and learn really these kind of latent correlations between different far away points of the measure, in this case of the graph, and are able to kind of do like a very accurate prediction on top of that. So this actually is, I think actually is going to be one of the frontiers for a lot of this simulation, especially the ones that are based on partial differential equations. However, that is not the whole thing. And one kind of much more general topics I want to bring up is that, as I mentioned before, the world of AI is getting actually a lot of investment, because there are a lot of applications beyond HPC that are really important, and actually that they get actually transformed by the use of artificial intelligence. At the same time, artificial intelligence models, in particular deep neural network models, are really exploding in terms of computational requirement. This is actually a graph, actually is not completely updated, is up to 2019 from OpenAI, where they basically charted on a log graph the size of different AI models over the last few years. And as you can see, it's not surprisingly an exponential increase, as most things computing. What is surprising is the slope of the curve, because the slope of the curve is effectively is basically much more than the normal Moore's law would predict. In fact, it's about 5 times more than what Moore's law predicts. So what this is saying is that the computational requirement for AI is increasing much faster than the normal computational requirement of the rest of the application. And that is why there is all this investment in accelerators for AI workloads. Now, we talked about that before, and AI accelerator for workloads may play and already play a very big role in accelerating HPC workloads. One thing I want to kind of bring up as a last point is that it's not just about the accelerator itself. It's also about cluster of those accelerators. And this actually is a requirement that is now very hot in the AI world. And those clusters of accelerators have reached actually massive scales. For example, Google has just announced at the last I/O that soon they're announcing it, the latest version V4 of our tensor processing units. But the pod, that is basically the cluster where this processing unit come with, has basically like 1 exaflop of computation available. And those things are for rent. They will be for rent actually kind of at the end of this year. And you can actually kind of come to a cloud provider and get one of these effective supercomputers for rent for a few hours to run your workload. And I think actually that is another transformation is about to happen. It used to be that supercomputers at this scale were really kind of in the realm of like, national labs or like institutional kind of entities. This is now becoming something that is much more democratized, where even kind of smaller companies, smaller players can rent one of these things for a little while. So again, this is part of the transformation that this word is bringing here. But I'll let Dosh actually take it again and kind of conclude actually this webinar.
So what, after so much excitement about present and the future, what can be done on Rescale platform today? So let me quickly showcase. Most of the software that we talked about earlier is already installed on Rescale platform. They are ready to run on GPU-enabled instances today. And in addition, we have all the machine learning, data science tools and frameworks readily available on our software catalog. These are some of the GPU-enabled hardware, so-called core types on Rescale platform. And we have from legacy to up and coming, we have all this hardware available for your usage. And finally, after especially the COVID lockdown, it has become a lot more important to be able to get a visually interactive environment for your workflow needs, either for graphics rendering or for interactive CAD and CFD, CAD and simulation workflows. We offer virtual workstations of various capabilities, meaning we have both GPU accelerated workstations that excel on graphics workflows, and we also have large compute, large memory, or large storage desktops, which are suitable for various needs for, let's say, mesh generation or high memory or high storage intensive workflows. We have all these options available. And in addition, we have technical documentation and support to get you started. For example, in deep learning, we have an entire section that talks about deep learning on Rescale. And with that, I will hand it back to Jolie.
All right, awesome. So this is just a reminder to everyone. If you have a question and you want to ask either of our presenters, now is the time to write that in the questions window, and we will get rolling with that. All right, so I'm just taking over screen share here, but in the meantime, okay, we got Massimo on camera. Dosh, I don't know if you want to join us. I'll jump on here too for our Q&A. Looks like we've got a few questions that have popped in here. The first one is from Arpita. She asks, when does it make sense to use TPUs versus GPUs?
Yeah, maybe I can take that. So one thing actually with tensor processing unit is that at the moment, they lack some of the library support that, for example, GPU has developed. Nvidia has done a tremendous work, for example, to enable scientific computation within CUDA. Now, at Google, we're working on some of that, and we're using, for example, have been releasing a framework called JAX within Python that allows to do a lot of like the computation that you do in scientific computation in terms of at least kind of linear algebra capability, things like Fourier transforms and of that kind. And we even kind of shipped experimental version, for example, of CFD simulators built on JAX. But I would definitely kind of recommend to kind of look at the kind of workloads that you're trying to do, see what toolings are available. I would target TPUs mostly for the very, very large scales. As I mentioned, like when you go to clusters, that's where TPUs pods really shine. But if you have smaller workloads, it's probably kind of much easier today to work at smaller scale with kind of GPU hardware, and that's already extremely effective.
Great. Thank you so much, Massimo. Cool stuff happening over there at Google. Another question, this one's from Jason. What are some good software applications for surrogate models?
I'll take that, Massimo, if you don't want it. Okay. So commercially, surrogate models, as I mentioned, has been around for decades. It's nothing new. Many of the commercial applications of big players already have some capability of surrogate models using more traditional machine learning techniques. If specifically we are talking about neural nets, I mentioned, there are some commercial tools that are picking up, implementing neural net-based surrogate models. And maybe the one that is forthcoming is the one that I mentioned in ANSYS Arsenal, that not only is talking about physics-informed neural net, but also using machine learning for surrogate models. So that was from last year, maybe they are incorporating that into their tooling today. In terms of platform services, again, those two companies I mentioned, Monolith and Neural Concept, seem to be specifically aiming at this problem. So there would be other commercial offerings that are out there that I am aware of. So I hope that answers the practical aspect of the question.
Great, thank you. Let's see. Oh, we have one more that's popped in here. Jenica wants to know, can you simplify how Google and Rescale work together for AI and what makes them a strong combo?
Maybe I guess we'll go on those.
Go ahead, Massimo, from your end.
I was just going to say actually kind of a few words, and then maybe if you can kind of take it more in detail. But one thing I would kind of call out is that from a Google perspective, Google is a little bit of a galaxy. It's a lot of things. So we have a super big area of research. Of course, we have all our consumer products. But then within Google, there is also Google Cloud, where we work around, how do we make our data centers available to other companies and other users that want to use the kind of computation that we have available internally. And so in that realm, we are not really like an HPC provider per se, and we kind of leverage a lot of partners, and Rescale is one of the biggest one in this area, in order to enable our customers to use our computation facilities and succeed in their workloads. Dosh, I don't know if you want to add something there and kind of.
Yeah, it's Rescale's value prop, not specific to Google Cloud, but to enable any of these CSPs for ease of use for the end user. So Rescale is a platform in between these cloud service providers, and that makes it possible for you to not to worry about installing this hardware, not to worry about benchmarking them, not to worry about maintaining them. Just get on the platform and use it. And that is purely from engineering perspective, but there's also accounting and IT side of this, keeping track of all the consumption, keeping track of usage. These are also very important aspects of using Rescale rather than directly using CSP. And keep in mind, CSPs offer different hardware and different levels of services very quickly, like they change their offerings and services. So today you may be going with one provider, and suddenly you may receive a credit from another provider and decide to use them. If you were a direct user of one provider, what would you do to move to the other one? You will have to write all that integration on yourself, learn about their APIs. Today, it's on Rescale. It's a simple matter of choosing another core type from the menu, and suddenly you will run in another different CSP. So I think that abstraction of CSP and IP issues from the end user is the key value of using Rescale here.
Great, thank you, both of you. We did have another question come in from Ronald. Has there been any recent ANSYS FEA-focused simulation plus AI learning for generative engineering workflows?
From my end, I'm not aware of generative design workflows on ANSYS. I do know Autodesk has been the spearheading that effort. For FEA and AI, I think in that slide, it's more of generic. So I can't recall exactly, but this is not limited to CFD. So any of these approaches, in principle, interchangeably applicable to FEA and CFD. So I would presume ANSYS is working on addressing that. Any additions, Massimo, from your end?
No, again, I'm also kind of not aware of anything specific, but if I remember correctly, as Simulation World, that is the main ANSYS conference this year, there were a number of talks actually about that topic. So I'm pretty sure that they're working on it. I would say it's definitely a question to ask ANSYS specifically if you're interested in an ANSYS specific answer.
All right, sounds good. It looks like that was our very last question. So we're going to go ahead and move to the conclusion of this webinar. Just a reminder that you can keep up to date on the Rescale platform by visiting social channels, same with Google Cloud. And you can find the Big Compute podcast at bigcompute.org or wherever you get your podcasts. And if you'd like more information or want to get in touch with Google Cloud or Rescale, here are a couple links that will allow you to do that. And yeah, with that, I don't know if we have any closing words from our presenters, so I'll just say thank you, Massimo and Dosh, for joining us, and for everyone out there for being here. It certainly has been a pleasure to spend this hour with you. And everyone out there, please stay safe and have a great day.
You too, Jolie.